Welcome to the New Chemist. We're glad you're listening. Feel free to download this podcast on Google Podcasts, Apple Podcasts, and Spotify. Here on the New Chemist, we discuss chemistry, which simply put is the science of change, as well as careers, community research, and COVID-19. We're happy you're tuning in. My guest today is Dr. Silas Cook. Thanks for joining me today. It is so good to hear from you. Just briefly, I'll inform my audience about you. Dr. Cook began his academic career at Reed College in 1995. After earning his BA in 1999, Professor Cook took a position at the Genomics Institute of Novartis Research Foundation in San Diego, California. There he worked to unravel various signal transduction pathways related to kinase and GTPase cell signaling. In 2001, he began his graduate studies in total synthesis at Columbia University in New York. Under the auspices of Professor Samuel J. Danishevsky, upon the completion of his PhD in 2006, he took a postdoctoral position in the laboratory of Professor Eric Jacobson at Harvard University. In 2009, Dr. Cook began his independent appointment in the chemistry department at Indiana University. Please welcome Dr. Thanks, Dr. Cook, for joining me today. It's so good to have you on.
So, Dr. Cook, to be here. I appreciate the opportunity.
Yes. So, Dr. Cook, what have been your longstanding interests in the field of science?
So I have pretty varied interests in the field of science. I think human biology is tremendously interesting, and I think chemistry is a great way to probe human biology. Non-human biology is also very interesting. Plant biology is very interesting. And I think chemistry is a great way to probe and understand plant biology as well. And so I think a lot of what drives our science or my thinking is how do we paint a clearer picture of how things work both within us and around us.
Okay, good. So in terms of a clearer picture, what specifically are you referring to? You said you paint a clear picture of those things around us and within us, or what
yeah, exactly. So how do things work, right? So okay. we have pretty vague general ideas of how certain cells work in concert in order to make up an organ, but we don't really have a good idea about how they communicate, what chemical messengers are used in communication in order to control a wide swath of cells that might be an organ or might be an organelle in plants, for example. Okay, so being able to understand those things, understanding how chemicals orchestrate huge numbers of cells on the order of trillions of cells at the same time, both in humans and plants, is tremendously interesting.
Okay, yeah, that's definitely true. So along the same line, or along the same direction, would you say your research interest first started there around the desire to create a clearer picture of what's occurring on in biology and chemistry, or would you say it was more from like your upbringing that caused you to have the research interest that you have now?
It's always difficult to pinpoint where your interest gets started, right? Because you're always refining your interests, becoming interested in new things, new ideas, new concepts. But I grew up on a farm, right? Okay. And I think as a farmer, you sort of have an inherent interest in how the world works and how things develop, both from a plant standpoint and from a human standpoint, and understanding how those things manifest, how they interact, how they get along, symbiosis, as well as trying to kill one another, is all based on chemicals. And so understanding these chemical messengers, these chemical communication that occurs between cells, is hugely important.
Yeah, I agree. So, along that same line, what have been your most effective and impactful ideas to date? What would you say have been some of your most effective and impactful ideas within the scope of your research or within the scope of your academic career thus far?
That's a great question, and I don't know if I can put a finger on a single event. I think probably some of our most impactful work in terms of being adopted by other chemists, being used widely in industry, came from my students. They're not my ideas, they're my students'
Okay.
ideas.
Okay.
And so I think one of the most important roles that I play is not necessarily coming up with ingenious ideas, but creating an environment where students can do their best, come up with their best ideas, and move the field forward. I try to um, create as many environments as possible where people can speak their mind without fear of condemnation or being belittled or anything like that, such that good ideas bubble to the surface.
Mm-hmm.
A great idea isn't necessarily great upon first inspection. I like to tell people that I have a trash can full of good ideas. It doesn't mean they actually worked in real life, right?
Mm-hmm.
And so actually getting an idea to work in lab is hugely important. And it's driven entirely by students, postdocs, undergraduates, the whole environment that we work in. Without that environment, we just have ideas on paper, and that doesn't mean anything.
That's true. It's very true. So, Dr. Cook, I know you've done a little bit, done some work in radical chemistry. So, why spend time researching radical chemistry?
So we spent a lot of time trying to teach transition metals that are good at radical chemistry how to do two electron chemistry.
Okay.
And it turns out that it's really difficult to teach these metals to do two electron chemistry when really what they want to do is single electron chemistry. And so it was around probably 2014 that I realized that we were trying to teach a fish how to climb a tree,
Mm-hmm.
and the fish realized it wasn't very good at that job. And so why not go with the flow and let the fish swim? And when we did that, we found that metals like iron and manganese are tremendous single electron redox wells of reactivity, and we can employ that reactivity to forge really difficult carbon-carbon, carbon-fluorine, carbon-oxygen, carbon-nitrogen bonds that we wouldn't be able to do with two electron chemistry that is traditionally used in palladium, even nickel, platinum, rhodium, ruthenium catalysis.
Okay. Okay. So, it's interesting that you say that, because when I hear about these one electron processes that we do in the lab that we use metals for, it almost seems similar to like what occurs in the electron transfer chain, in which you have iron sulfur clusters and stuff like that. So, definitely interesting. So, in layman's terms, what impact does this work within you? This work with radical chemistry, what impact does it have?
So
Or what are the
we
implications?
Right. So in layman's terms, we're interested in making bonds that people care about,
Okay, that's
right?
good.
And so the pharmaceutical industry, the agri-sciences industry, the academic industry, the materials industry are all trying to make things of relevance. If you're in the pharmaceuticals industry, you might be trying to make a small molecule drug. You might be trying to make a macromolecule. But the bottom line is you're trying to make new bonds of interest, right? You're trying to create chemical matter that will modulate whatever activity you might be interested in. And that's true of agri-sciences, that's true of materials. And so if you look at Lipinski's rule of five, right, where molecules, small molecules under a molecular weight of 500, C log P of greater than a certain benchmark, and so on, you have roughly 10 to the 60th organic molecules that you can make. And so 10 to the 60th is a pretty large number. Most people aren't used to working with numbers on that scale. But to put it in perspective, right, the universe is about 4 times 10 to the 18th seconds old. And so that means you could make a new molecule every second since the Big Bang occurred. And you wouldn't even be scratching the surface of potential small molecules that fit Lipinski's rule of 5. And so another way to phrase that is you could spend your entire life making molecules no one cares about. So why not make molecules that people care about? And so we really take our cues from medicinal chemists, from process chemists, across a wide range of industries to see what they're struggling with, to see what bonds they have to take multi-step to get to. And we try to simplify that. And radical chemistry, with the transition metals that we use, tends to simplify synthetic sequences. And so, what used to take 5, 10, 15 steps to make, we make in 3, 4, 5 steps.
Wow, that's good.
And that makes a big difference to practicing organic chemists, people out there in the real world that are actually trying to access a specific chemical environment, a specific chemical space. And so we take that very seriously. And so we're constantly combing through the medicinal chemistry, the process chemistry literature, looking for areas that are underdeveloped, areas that process chemists or medicinal chemists are struggling with. And we try to improve both step counts, yields, and obviously synthetic
utility
effort to get there.
Okay. So I have a question along those same lines. Would you say that your radical chemistry is more effective in the realm of hydrogen abstraction or carbon-carbon bond formation, or which bonds do you say primarily are the ones that it really has the most effect on, or it really has been beneficial for?
So certainly CH functionalization has been important to our group over the last 5 or so years, right? And I do think being able to take common heteroatoms, oxygen, nitrogen, sulfur, and using those heteroatoms to abstract hydrogen atoms nearby to then reveal a carbon-based radical that can be functionalized with transition metal chemistry to forge new bonds has been hugely important to our group, and to a lot of other groups as well, right? And so David Naguib, Jenny Roizen at Duke University, and others have used this hydrogen atom abstraction technique to functionalize sp3 hybridized CH bonds. Prior to our work and others' work in this field, generally you would use a 2-electron, 3-atom oxidative addition type mechanism to functionalize a CH bond. And that worked quite well for sp2 hybridized CH bonds, but it didn't work so well for sp3 hybridized carbon atoms. And so this hydrogen atom abstraction and functionalization really took off once you used H-atom abstraction as the tool to functionalize those sp3 hybridized systems.
Okay, yeah, that's good. So going in a different direction, how do you maintain view of the bigger picture in your career and in your life in general?
Yeah, I wish I knew the answer to that question. I really don't. So as I mentioned previously, I like students directing their own projects, right? And so I really try to act more as a consultant on their work,
Okay.
as opposed to an advisor that has a top-down iron fist approach to their project. And so a lot of times projects develop in unusual ways that I didn't anticipate at the outset. And students really make the big picture decisions on where to take that chemistry. And I'm just along for the ride. I just sit back and get excited about the work. And so for me, I don't know that I have so much a big picture, steer everything in a certain direction approach,
Okay.
as I do sit back and let the smart people in the room, namely my students, take over and dictate
Okay.
decisions and directions for a project.
Okay. That's definitely one approach. It seems as if you kind of just let things flow naturally. Then.
Yeah, I mean, they zig and they zag, right?
Yeah, that's true.
Sometimes projects we have that seem very, very exciting, are moving in the right direction. We're over the moon about the potential, that end up in a burning car crash at the bottom of a hill, and
Wow.
that happens, right?
Yeah.
And there's not much you can do about it. The science is what it is. But there's other times where we think things, a relatively sleepy result, not very interesting, ends up driving a whole new wing of the group, and those are very exciting. And so the most important thing is just to keep an open mind.
Yeah.
Right?
Yeah.
Keep an open mind, let the data soak in, and go where the data tells you to go.
I agree. Yeah. So I have a question. What would you say has been a big player in your research exploits? Would you say the fundamental science concepts, or would you say the advanced ideas that take place within the literature? Or what has been like overarching thing? Because from my understanding, from my discussions with other people, it's talk about how fundamental science plays a large role in what they do on a daily basis.
Sure, I think fundamental science drives everything at the end of the day.
Okay.
But day to day, you might have a plan in order to achieve some outcome, but you have to be able to throw that plan in the trash and move with what the fundamental science tells you to move on. We're interested in new information, certainly, right? I mean, we all want to refine and develop a better understanding of the world around us. And we do that through shrewd experimentation. That said, you can spend a lot of time developing a fundamental understanding of something no one cares about.
That's true.
And so don't do that.
Okay.
What you want to do is spend some time trying to develop a fundamental understanding of a process, a reaction, a biological phenomena that people care about, right?
Okay.
You brought it up earlier in terms of single electron chemistry, but the Krebs cycle is
Okay, let's go there.
hugely important, right?
It is. Yeah, from citrate to oxaloacetate.
And there's a lot of beautiful chemistry, beautiful biology that was developed along the way to understand the Krebs cycle. And that is a completely meritorious, work on the TCA cycle, understand how that works, because it is so fundamental to the world, that it warranted the extra time spent developing carbon labeling studies to follow the carbon footprint and the Krebs cycle, to work out the stoichiometry. All of that was fundamental science, but it was on a process of huge importance.
And so oxidative.
Exactly. So if you have the right problem, you can pull out all the stops and study the smallest of details in that process, and all of it benefits mankind, right?
Yeah, that's
But
good.
but if you work on something nobody cares about, you can still
Agree.
pull out all the stops. You can still
Mhm.
spend a lifetime working out the details. But at the end of the day, if no one's going to use your technetium catalyst to do
Mhm.
what you spent a lifetime working out to do, it doesn't
Mhm.
really matter.
That's true. It has to have so societal relevance. My question to you is, how do you maintain, given that you allow your students to uh, kind of direct certain projects, how do you maintain vision and teamwork in your environment? How do you make sure that everyone's working together? There's a collaborative spirit within your group. How do you maintain that?
Yeah, that's a great question. And I think that's an ever changing question,
Okay.
certainly in the time of COVID. Um,
Yeah, I agree. I agree.
and so I wish I knew the magic formula that would breed cohesion in the group. But to be honest, I think I failed my group during the time of COVID. We used to have a lot of group activities in terms of problem solving, idea generation, um, subgroup meetings, all of these things where we could get together in a room with a chalkboard and develop ideas and develop hypotheses. And I was never really able to recapitulate that in a virtual environment. And I would say that probably morale in the group is at an all-time low. We've done online Zoom type activities. We've tried problem solving online. We've tried idea generation online, and it just does not work the same as everyone being in the same room with a chalkboard or a couple sheets of paper and a pencil. And so it's been difficult.
Yeah, I would say, it's good that you're being honest, Dr. Cook, but I would say this, at least one thing I can understand is, challenges to allow us to grow, eh? To allow us to provide a platform or impetus for growth. Yeah, so it's definitely, I appreciate your honesty, because some people like to paint a picture that everything is peachy, dandy, rosy, and fine. But
It's
if
not.
it's not, it's not. Yeah, because COVID has been challenging for everyone, at least from everyone I've encountered, I should say. I can't speak for everyone, but people I've encountered. Yeah, COVID has been a challenge, especially
Yeah.
within the academic context.
I think that's right. I think the challenge is actually being understated, quite frankly.
Oh,
You have these big industries like, for example, accounting, banking, finance, computer science, for example, Silicon Valley. All of these industries have been pretty recalcitrant when it comes to offering online or at home sort of Zoom working environments. And
mm-hmm.
those are the areas, those are the careers really that could benefit, quite frankly, quite a bit from being online, from being virtual, right? I mean, you can do an Excel spreadsheet virtually. As you're editing it, other people can be looking at it. Everybody knows the syntax of Excel. And so it's actually quite amenable to at-home work or virtual work. Chemistry is not,
Yeah, that's
right?
true. That's
Our
true.
environment very, very different, right? We're more like a 3M or a Boeing or some of these companies that actually have to make things. And you can't do that at home, right? You can't take a 5-piece ton of titanium and hammer it into a plane in your house, right? That has to be done in a foundry. It has to be done in a proper location, and it requires the coordination of a large number of people. We're fortunate in academia in that our groups are relatively small, but at the same time, it requires a high level of collaboration. of discussion, of, face-to-face interaction, in addition to the long hours at the hood, the long hours doing experiments. But if you have an experiment that you're going to set up, for example, that takes 3 hours to set up, you probably want to run that idea by 1 or 2 other people before you spend 3 hours setting it up.
Yeah, that's true.
Right. And so losing that, immediate feedback loop, being able to bounce ideas off your lab mates, bounce ideas off of me, for example, just wandering into my office and asking a simple question about a simple reaction, all of that being gone has hurt research. It's hurt progress.
Wow. So what's the plan then, Dr. Cook? I take it you haven't been able, you have not, I take it you have not, not considered a plan. What is the plan of action? I think a man of your expertise has probably some plan of action, or has already enacted a plan of action already.
Right.
What's the plan?
So before I give you my plan, I want to give you a piece of data that I find pretty interesting. So I taught 2 courses this spring semester, spring of 2021. One was completely virtual, completely online, and one was entirely in person. I recently got my teaching feedback, so these questionnaires that we send out to students about the difficulty of the class, what they learned in the course, whether they had sufficient access to the professor, whether the learning objectives were clear and met during the course of the course. And it was interesting to, in the same time period, compare this completely online class with a completely in-person class. In the completely in-person class, I got my standard reviews, which are, this is a very difficult class. The teacher was completely dedicated and made the information clear and understandable, even though it was complex. And I really enjoyed the course. I would highly recommend it to other people, etc. On my online class, it was the exact opposite. This was the worst class I've ever had. The teacher didn't make learning objectives clear. The teacher wasn't clear about the information being disseminated, etc. And so it's really interesting to see that I need more training on how to develop a more successful online course, which doesn't surprise me. But just the dichotomy between online versus in person, the same sort of information, the same delivery just does not translate over Zoom.
Yeah, that's true. And I think that sentiment is true in a lot of different areas, and it's true for a lot of different professors as well at other universities too. I've heard similar sentiments from my friends who are taking classes on Zoom, as well as my siblings who I have who are in school. They talk about how challenging it is to sit under Zoom instruction for hours and hours in high school. So I can even imagine when the concepts become more convoluted and more difficult, it's even more challenging.
Right.
Yeah.
That's right.
So,
so I've also heard the opposite though. And so I was talking to a faculty member in the Kelley School of Business this morning at a meeting I was at. And he said that actually his online courses get reviewed better than his in-person courses. And his hypothesis, which was presented to him by a colleague of his in the Kelley School of Business, was that he is much more intimidating and seems like a bigger asshole in person than he does online. And so, and so his online reviews were actually better because he comes across as an easier to understand and get along with human being over Zoom than he does in person.
Okay, well that's a different perspective completely, very different. Yeah. So in terms of, as we wrap up, Why did you choose chemistry as a field to major in? Was that because of your upbringing on the farm, or was it because you had a mentor, a high school teacher? What caused chemistry to be the particular for you?
Yeah, so that's a great question, and I wish I had a short answer, or I could say Mr. McReynolds in high school or whatever.
Or McDonald or something like that.
Yeah, exactly. But my answer is a little more convoluted in that I was always interested in science growing up, certainly. In high school, I probably had the world's worst chemistry class
Wow.
available in high school. So my high school chemistry class was taught by an assistant coach of wrestling at my school, and wrestling was a really big deal at my high school. We would send people to the Olympics, for example, straight out of high school
Wow.
from my wrestling team. So wrestling was far more important than chemistry, so much so that we only had 4 textbooks for the entire class of 30 high school students that took this chemistry course. So the wrestling coach thought it made the most sense to bolt those 4 textbooks to the benches in the chemistry lab. And we would spend our chemistry class reading with 6 or 7 people around the same book, chapter by chapter, every class.
Wow.
It was awful. And so certainly high school chemistry did not turn me on to chemistry. What did turn me on to chemistry is I was able to double major in chemistry and biology in college. And then I was fortunate enough to take a position at Novartis in San Diego after college, where I was able to do in the lab both fundamental biology and organic synthesis. And what I learned during my undergraduate and my time at Novartis was that the questions you can ask in biology are very, very interesting. But the actual experiments you need to do in the lab to answer those questions are very, very boring. And so running PCRs, growing up E. coli, mammalian cell transfection, whatever it may be, is not very interesting. And moreover, if you're going to be isolating some DNA that you grew up in some bacteria, you take an Invitrogen kit that says use buffer A for this procedure and buffer B for that, and you don't even know what's in those buffers. So it was very black box and not very interesting. Whereas in chemistry, you can test your hypotheses very, very quickly, I learned. And so if you have an idea, if you think that you can make a bond or break a bond, you can go in the lab, mix some chemicals together, and then take an NMR, take a GC, take a mass spec, and literally within a couple of hours be able to test pretty profound hypotheses very, very quickly. Moreover, if you need to do a particularly difficult experiment, you might need to blow some glassware, right? And so you can learn how to blow glass, you can learn how to make instrumentation, you can learn how to make custom reactor setups to run a given reaction if you think stirring or light permeance might be an issue. And all of that is, in my opinion, great fun. And so I learned pretty early on that the day-to-day life in chemistry is a lot of fun, and you can test hypotheses very, very quickly. Whereas the day-to-day in biology is pretty boring. And every 6 or 10 or 12 months, you might get an answer to a question you asked 6 or 10 or 12 months ago, which is a little too slow for my ADHD brain.
Okay, sure. So my final question to you, Dr. Cook, this has been definitely an interesting interview, to say the least. Yeah, so I appreciate your honesty, really do. It's very timely. So what has been some of the most beneficial advice you have received? You're obviously you're doing a good bit of work doing research. You're full professor at IU, which has a really good chemistry department, and I'm not just saying that because I'm here. Um, yeah, I think that to be true. So, what has been some of the beneficial advice, or the most beneficial advice you have received?
I I've received such great guidance from the mentors I've had in my life. Quite honestly, uh, at the undergraduate level, Pete Schultz at Novartis was just a tremendous mentor and had the most sage one-liners that you can possibly think of. I really enjoyed that. My PhD advisor, truly, truly amazing intellect, and again, outstanding one-liners. Um, for example, one of the great pieces of advice I got from my PhD advisor was to just make the bond. Just put the two pieces together, glue them together if you have to. And so I wasn't quite clear on what molecular glue I would need to use in order to make the carbon-carbon bond I was faced with. But definitely he had some good one-liners. And my postdoc advisor as well. I mean, I've really been fortunate to be blessed with great guidance all along the way. And even once I started my academic career, not only did my PhD advisor and my postdoc advisor continue to give me great advice, they also, taught me how to seek out the advice I needed to be successful in my own career. Right? There's no one person in your life who is going to be your mentor in every aspect of your life. Mm-hmm. Right? You're going to need an advisor for committee assignments. You're going to need advisor for grant writing. You're going to need advisor for new research directions. You're going to need an advisor for your personal life. All of these things are different people.
So yeah, I appreciate that. And just as we conclude, you made I wish we had met Oxford. I wish I had asked this question earlier because you made the statement, seeking out people that would give you the right advice or the advice that you need. How do you go through that process? How have you done that? Is it just through experience, or is it through like you inquire, or was it that's a guiding principle behind you?
So I wish I could give you a succinct answer, but in my experience, in my life, one of my greatest strengths and one of my greatest weaknesses is that I don't get embarrassed.
Okay.
And so I don't care if I feel like a fool or look like a fool in front of anyone. And so
that's powerful. That's powerful.
That is powerful. I can walk into anybody's office, no matter how high or low ranking they are in the world, and ask a dumb question. I feel perfectly comfortable doing that. And most people don't, I've learned. And so the drawback is that I don't actually recognize in other people that they might be reluctant to seek advice or reluctant to look like a fool in front of me or in front of someone else in the room. And that's been a challenge for me to try to navigate, to try to draw people out of their own shells to, seek the advice that they need, right? And so it's not often obvious what advice is going to tip the scales in your favor. And so you need to take a lot of shots on goal. Sometimes you're going to ask for feedback from someone who really doesn't give you the feedback you need. But you listen patiently, you assess that feedback, and you decide, is this someone I'm going to come to again in the future or not? Mm-hmm. Right? And so, in that way, I've probably sought out 100 mentors, and I probably only have 3, right?
Yeah, that's fair.
So, sometimes you have to look like a fool in order to get the information that you need to make the best decision that you need to make, whether it be in your personal life, professional life, grant writing, student recruiting. I don't care what the topic is. right? Some people are going to have good advice and some people are going to not have such good advice.
Thanks for listening. We're glad you were able to tune into this podcast. Once again, this is The New Chemist, where we discuss chemistry, which simply put is the science of change, as well as the other sciences, careers, community, research, and COVID-19. Thanks again for listening. Note, the views on this podcast represent those of my guests and I.